This week we're going to look at a short example on slope staking roads. Before we get into that, I just wanted to touch real briefly on a new unit of measurement that we're going to talk about with roads. We threw this around a little bit up there in Thompson Park when we laid out centerline, but that's stationing. And when we deal with highway projects, sewer lines, excuse me, water lines, really any kind of linear project, stationing is what's used to identify where you are on the job site. And stationing is just simply, it's another unit of measurement, just like a foot, meter, or centimeter. And one station is equal to 100 feet. And we designate a station with, you can kind of see that digit plus something after that digit. And the first digit refers to how many stations you are, and then the plus sort of serves like a decimal point, where the numbers after the plus represent a portion of a station. So you can see here at the very beginning of our alignment, we're at 0 plus 0, 0. And then at 25 feet, we would call that station 0 plus 25, because we have not yet surpassed one whole station. 0 plus 50, 0 plus 75, and then up at 100 feet, we achieve station 1 plus 0, 0, or 1 plus a pair, right? A pair of zeros. And then that process just repeats itself. At another 50 feet, we'd be at 150 feet from the beginning. You're at station 1 plus 50, 2 plus a pair. And then you can get just as precise with your stationing as you can with a traditional linear measurement. You can go to the nearest hundredth of a foot. So station 2 plus 70.32 or 3 plus 37.50. Measuring the distance between stations, which is real common, what you would do on a takeoff or an estimation assignment or project. He'd want to know what's the distance between station 0 plus 75 and 3 plus 37.50. You set it up just like a normal arithmetic problem, but you get rid of those plus signs, right? So you're essentially taking 337.5 minus 75 for 262.50 linear feet between those stations. This is a typical kind of roadway cross section along one particular station, of a roadway project. And the green line represents what I would call the natural ground, or the existing ground. And the blue line represents the design feature. The design feature. So the geometric surface, or the line that has a equation, like we talked about in the definition of a slope staking last week. If your cross section has both a fill side, which is what we have on the left, and a cut side, which is what we have on the right, you're going to have slightly different geometry left and right, because a fill side does not need a ditch. You can just go straight from your driving surface and shoulder down to your catch slope. But on a cut side, right, we do need a ditch. Sorry, there's a little lag here with my pointer. There we go. On the cut side, you have your driving surface and your shoulder, and then you do need a ditch. So your cut side is always a longer or a wider geometry before you get into your transition slope or your catch slope, right? It's pretty typical to have a crown, especially if it's a paved surface. 2% is the kind of the minimum slope needed to shed water in a rain event or when snow is melting, right? You don't want that melt water during a warm-up on a winter day to pool and then freeze and turn into black ice later that night. So you do want that rainwater and meltwater to shed off a crowned surface. Um, Pretty typical to have a shoulder, just for that kind of safety factor for your tires if they get off the driving surface. And then a little ditch to handle that stormwater runoff on your cut side. So we're going to look at just a couple pictures of what slope staking kind of looks like, or slopes look like when they're cut into the ground. This was just a little logging road in the Gallatin Forest I took some pictures of a few years ago, and real simple cross section here. You can see the slope of the natural ground, where I don't know what that is. That might be a 2 to 1 or 3, not that steep. It's 3 to 1 or 4 to 1 coming up, and here's where you would catch back into the natural slope. And then designed roadway was cut into this, where we've got a nice 1-to-1 steep slope, pretty flat driving surface, and then probably another 1-to-1 here, and then we catch back into the natural slope. This illustrates something that you kind of develop a feel for when you're slope staking, is the higher your natural ground surface is along a station relative to the design surface, right, the center line out here where you're staking, the longer that transition slope, or the longer it's going to be before you catch. So you can see over here where the natural ground comes down quite a bit lower and is almost equal in elevation to the design surface feature here, you have hardly any catch slope at all. This is a little better illustration of that. Up here on the steeper, or not on the steeper, but the higher part of the slope, we have a long catch. Down here where the natural ground is dropping in elevation, not much catch at all. And that's really apparent here on the I-90 cut. You know, this is the cut you recognize when you're driving from Whitehall to Three Forks, heading east. Real steep, or real high ground compared to the design surface, which is your asphalt down here, and you can see that catch slope had to go back quite a ways before it caught the natural ground. I think what they did in here, these little flat benches, are just because of the stability of the ground and how steep they had to go with their cuts. They serve as kind of a rock catch, so that those rocks falling don't land on the roadway. And actually, this is another good excuse me, illustration here. They went really steep with this slope. This is steeper than a 1-to-1. This might be a 1/2 to 1, where you're only going a 1/2 of a horizontal foot for every 1 vertical foot, right? That would be the expression, a 1/2 to 1. And you're doing that because when you have this steep of a slope to cut into, you don't want to be chasing that at a gradual 1-to-1 or 2-to-1 or 3-to-1 slope, right? You'd be going back here forever and ever and ever, moving all kinds of material, and you'd have to purchase a lot wider right-of-way from private landowners. So steeper slopes can be used to kind of minimize right-of-way purchase, minimize excavation, but then something like this barrier protection is needed. Or when you travel to, I think you see them on I-90 going into Washington, literally like netting, or chain link cages kind of holding back the rocks from falling. And then this is a picture that kind of shows the whole kit and caboodle. If we look off in the little bit of the distance here, you've got this cut slope on your left. It goes down to like the ditch bottom, and then you've got this nice big wide design element that encompasses 2 lanes plus a center drainage ditch. So you've got some sort of slope coming up to the driving surface here. You've got your crowned asphalt surface. You've got a drainage ditch down and up. You've got another crowned asphalt surface. You've got a recoverable slope down to a toe and then up to your catch point. And what's interesting about this is even though the distance between this toe and that toe is really, really wide, you still only have two hinge points, right? And two variable slopes. So you only have, again, two catch points to worry about, even if you're staking out a complex road like this as opposed to the very basic forest road that we just looked at a couple slides ago. Another thing to point out in this picture is we've generally been looking at pictures where a design is cut into a side hill where you're balancing cuts and fills left and right. Well, this is a scenario where you're actually balancing cuts and fills up and down station. And up station means you're getting further away from your starting point. Down station means you're coming back closer to your starting point, 0 plus 0, 0. But here, over by these guardrails here, from the left, which was a cut, all the way over to the right, which was a cut, that's an entire section of cut material, right? Because you can see where the natural ground used to be. You came across the top here, straight over, go probably 10 feet above the roadway surface, and then it connected back in here where the ground is today. So they didn't haul any material left or right, but it looks like they hauled it down station closer towards us, where down here in this little valley, this is all fill scenario, where it's out of frame here, but you've got a catch point that's actually a fill slope coming up. Then you get into your designs, and then you're going to fill back down to your catch point, which is again out of frame here. So you can move material left or right, or you can move material up or down station along a job site while you're trying to balance your earthwork. And that's what we start to get into here in the next couple weeks, is earthwork quantities. This is the last picture here. I took this just last week, Thursday. I was tying up some ends on a survey job I'm doing over in Big Timber. And this is it's a much steeper driveway than it looks in this picture. The road itself is probably going downhill at a 5 to 6% grade, and then the cross slope that it's cut into here, that's easily a 1-to-1, just the natural slope. And Ken asked a question in the forum discussion this week about, he was kind of leading the witness. He knew the answer to it, but he wanted to ask it so that I could address it for everybody in class here. Is it possible that your cut slope or your fill slope will never catch? And that's entirely possible, and that's a very realistic possibility in terrain like this, where if you've got a 1-to-1 natural ground slope, right, going down the hillside, and you want to cut in a road surface like they did here, and then transition in and catch it with the fill slope on the downhill side, if you're trying to tie into a 1-to-1 natural ground with a gradual 3-to-1 slope, right, you're just going to stay above your natural ground forever and ever and ever, and you're never going to catch it. Same thing on the uphill side. If you've got a 1-to-1 natural slope going up, and you're down here at your toe, and you're trying to chase it back at a more gradual 2-to-1, you're just going to be buried below that surface for forever and ever. You're going to be chasing yourself uphill, and you'll never daylight. So your design slopes have to be steeper than your natural ground, or else you'll never catch. So let's look at an example. Throw some numbers on this, and I'm not going to go too deep here into the weeds, because I think slope staking is an exercise that makes the most sense when you actually execute it excuse me, on the ground. which we'll do this Friday up there in Thompson Park. But I wanted to go over an example of the math and show you just how they can be, the equation's a little different left or right depending on your cut or fill scenario. So remember, these steps over here, these are the 6 steps in going through slope staking. Is first you want to identify what I call the hinge point of your cross section. You want to determine the elevation of your hinge point, and you want to know what the distance is from the center line out to your hinge point. Then you're going to measure a guess along the existing ground from the center line. You're going to measure the ground elevation at your guess, and then we're going to solve for the general equation. So let's go through that first with the left side of this station. We've identified the hinge, which is right here. And again, the hinge is just the last point in your geometry before you hit your transition slope out to tie into natural ground. So it's the edge of the shoulder there. The elevation of the hinge is based on your design elevation. So we've got a centerline design elevation of 102.50 feet at this particular station. You can see we have a 12-foot driving lane, a 2-foot shoulder, both at 2%. So we've got 14 feet at 2%. We're losing 28 hundredths of a foot from our center line. So our hinge elevation is going to be 102.22. The hinge distance from center line is going to be 14 feet, and that's your L distance when we get to the slope stake general equation. Next is to guess a distance, and this is literally us pulling a cloth tape. We're going to guess, in this example I'm just going to say 18 feet out. One thing is you already know what your minimum guess has to be right now, right? You have to be guessing at least your L distance, 14 feet. Because even if your natural ground happened to be at the exact elevation, 102.22, you're still going to be at least 14 feet away from your center line just to have your driving lane and your shoulder. So you always have to go further than your L distance with your guess. Next is we measure the ground elevation at the guess distance. And I just had to throw in an example number here of 101.35. How you come up with that can be with any tool that you know how to use now to perform vertical measurements. A hand level with a Philly rod, an auto level with a Philly rod, GPS, total station, doesn't really excuse me, doesn't really matter. Anything to give you that ground elevation out there where you're standing. And then we want to solve for the general equation to solve for this x distance, right? And remember, the general equation is x equals L plus slope times your cut fill. Well, if we add our known variables into that now, x equals L distance, which is 14 feet, plus, we're at a 3-to-1 slope, so our slope value is 3, and we're going to multiply that by the cut fill dimension. And that cut fill dimension is nothing more than the elevation of your hinge minus the elevation of the ground, because that's the vertical dimension, right? That's the cut fill vertical dimension to get from hinge down to the ground surface. And when we multiply that vertical distance by 3, because it's a 3-to-1 slope, right, that's giving us the horizontal equivalent of how many horizontal feet it'll take us to achieve that vertical separation at a 3-to-1 slope. So come back down to the equation. L 14 plus slope 3 times 102.22 minus 101.35, or 14 plus 3 times 0.87 for an x distance of 16.6. And you come back up here. X calculated based on that ground elevation does not equal the distance that we guessed. And when x does not equal your guess, you did not find your catch point, right? X caught a lot sooner based on that elevation. We guessed 18, it caught at 16, which means X is shorter than our guess, so we move in closer, pick a new ground spot location, and we guess again. If your ground elevation is not changing, you know you need to come into exactly 16.6 feet, and you'll find your catch point. But what's typical on a cross slope like this is as you move in for a new guess point, you're also gaining elevation. And if you're gaining elevation, this part of your equation is going to change, which means this value in your general equation is going to change, which means you're not going to be 16.6 again. You're going to be something even smaller. So that's where this becomes an iterative process, is maybe you were 2 feet short, but you can see that if you come in closer to center line 2 more feet, you're gaining a half a foot elevation. Half a foot at a 3-to-1 is 1.5 feet, so maybe instead of coming in 2 feet, you come in 3.5 feet, right? That's where you just get a feel for it after you do 1 or 2 stations. And you'll also start to realize after we do this in person a couple times, is you run through this equation in your mind. You're not out there with the calculator. You'll slow yourself down. You'll slow your crew down. You don't want to be that person who needs a calculator in their hand when they're doing slope staking. So get comfortable doing this in your head, because that's the way you'll have to do it. So let's look at the right side this time. We're going to go through the same steps. Identify the hinge point, and it's this point right here. Just because I threw in this 3-to-1 designation on that slope doesn't mean it's a variable slope. It's a 3-to-1 for a standard 1-foot ditch, which means you don't get to a variable slope that will be catching your natural ground until the bottom of that ditch this time. This is the only variable in your geometry. So the elevation of the hinge is a little different now. On the right side, it's your centerline elevation minus your 14 feet at 2% for 2800s, minus 1 vertical foot for a 101.22 design elevation. The hinge distance, a little different again this time. You've still got your 14 foot, 12 foot lane, 2 foot shoulder, and now we have a 1 foot ditch at a 3-to-1 slope for 3 more horizontal feet. So we're actually out here at 17 feet for our L distance in the general equation. Just throwing in an example distance, we're going to guess 21 feet, right? We know we have to be at least 17 feet, so I'm going to guess 21. And using whatever tool I have available, I've measured the ground elevation to be 105.90 feet. Now I'm going to solve my general equation for slope staking. X distance down here is the computed distance, and X equals L times plus slope times cut fill. In this case, our slope is 1.5, because it's a steeper slope on the cut side than it was over on the fill side. So X equals L, which is 17, plus my slope, which is 1.5, times the cut fill dimension. This time it's a cut, the other side it was a fill, but it's still the same principle. Your cut fill dimension is just the vertical separation between the natural ground where you took your guess down to the elevation of your hinge point, right? That vertical dimension. We're going to multiply that vertical dimension times our slope number to give us the horizontal equivalent. So we have 105.90 minus our 101.22 hinge elevation, and we're going to multiply that by 1.5 for a total of 17 feet plus 1.5 times 4.68 equals 24 feet for our solved for x distance. Well, 24 feet is longer than what we guessed, so we're not out far enough. So your next iteration tells us you're going to have to take your guess point, move back, and repeat the process. So I know this might be a little confusing to you looking at it on screen, or actually maybe it makes more sense to you looking at it on screen, and the confusion will come when you try and do it out in the field where you don't have a picture to look at. But slope staking really is an exercise that has to be done in person. So that's what we're going to be doing this Friday.